So hello everyone, I am Rajarshi. I am from the Max Planck Institute for Software Systems, and today I will be talking about some new techniques for synthesizing formal specifications, specifically for runtime monitoring applications, but it could have many more applications. So this is a joint work with Daniel from TU Dortmund, Guillermo and Ritam from University of Antwerp, and Nathanaël from University of Bordeaux. So as I mentioned before, since runtime verification forms a major application area, I will begin with a brief description of runtime verification. So it is basically a collection of methods which are designed to detect bugs, failures, or violations during runtime. So I will explain this using a simple demonstration. So imagine you have an autonomous vehicle and you would obviously like to ensure that it does not crash. So for this, you can use runtime verification to monitor whether it triggers a brake when it reaches the unsafe distance of another vehicle. So runtime verification would detect a violation if it does, and it would report it to the human user to take immediate action. So one thing is common among all verification techniques, that is that they rely on formal specifications. So formal specification is an unambiguous way of writing the property that you want to describe, so the property that you want to monitor or check. But one point that is often overlooked is that formal specifications are hard to write. So they are tedious and they could also, writing them could be error prone as well. So I will demonstrate this fact using the same example of the autonomous vehicle. So the property that you wanted to monitor was that the vehicle triggers brake when it reaches the unsafe distance of an obstacle. So here I attempt to formalize it as a specification. So this specification uses globally and finally. So these in temporal logic refer to always and eventually respectively. And what this specification says is that always it is the case that when the vehicle reaches an unsafe distance, eventually the brakes are triggered.
In time.
Yes, so this is the important fact. So if one does not mention the time duration, it could be disastrous because the brakes could be triggered too late. So to tackle this, we introduce some time intervals. So now it says that the brakes must be triggered within 1 second of reaching the unsafe distance. However, if you have driven a car, you need to press the brakes for a certain duration. So to incorporate that, you need a slight modification. So now this specification says that the brakes must be pressed for a duration of half a second within 1 second of reaching an unsafe distance. Now if you look at this specification, for a human to get this correct would be almost impossible. So there are the structural parts, there are intervals. So this is what makes writing a specification very hard. So our goal in this work is to automatically synthesize specifications for the purpose of verification. And I will be looking at a specific specification language, Metric Temporal Logic, which is a popular specification for specifying properties in cyber physical systems. So this Metric Temporal Logic is a real-time extension of Linear Temporal Logic. So it is built over propositions such as reaching an unsafe distance, brakes getting triggered, and so on. And then there are Boolean operators, which represent Boolean combination of properties. So this could be and, or, and the standard Boolean operators. And then you have the temporal operators, which help you to represent properties involving time. So you have the time finally, FAB5, which says that phi must hold within the interval AB. Time globally, GAB5, which says that phi must hold during the entire interval of AB, and time until, which says that phi until AB the side, which says that psi must hold in the interval AB, and until then phi must hold. Now, the works that exist in the literature, so some of the works look at the parameter search problem for MTL, which is given an MTL formula of a fixed structure, the structure is fixed, they would search for the interval values. So they do not search for the structure of the formulas. On the other hand, there are works that can search for arbitrary structure LTL formulas. But since LTL does not include intervals, they could not search for the intervals. So our work would tackle both of these. So we will search over both the structure and the parameters of the MTL formulas. So the works I described so far usually use examples of executions of the system for inferring the specifications. So we would also do the same. We would consider a sample of system executions. In particular, we would consider a sample which consists of a finite set of positive executions and a finite set of negative executions. The positive executions would represent the desirable behavior of the systems, and the negative ones would represent the undesirable behavior. And this altogether we would call a sample. And since we are dealing with continuous time logic, our executions would be signals which provide the value of the propositions at each real value time points. However, continuous signals are difficult to extract from the system. If you have the system, you would not know exactly what the signal that the system is satisfying. So what we do to mitigate is that we have a finite number of observations, and using these observations, we create a continuous signal by extrapolation. In particular, we create piecewise constant signals, which are signals in which the values changes only in a finite number of time points. So let's look at our previous example. So here I would use p instead of unsafe distance to maintain to make it smaller. So here in the 0th time point it reached an unsafe distance, in the 4th time point it did not. So what it would mean in a piecewise constant is in the interval 0 to 1 it was in an unsafe distance, from interval 1 to 2 it was not, and so on. So we have this sample of executions as examples. Now, given a sample, there are many ways to find a specification. So we need to refine our search. So we consider searching for small formulas because they are faster in verification and they are more easy to understand, more interpretable. Also, we want formulas which are low in future reach. So what is this future reach? So future reach is basically a measure of the look ahead of a formula. So it tells you how far in the future can a formula look at. So for example, the future reach of f01p is 1, which means that f01p cannot distinguish signals beyond time point 1. So if you have two signals which are exactly identical in the first time point, then it would have the same satisfaction for f01p. And this criteria is often shows up in the complexity of runtime monitoring algorithms. Moreover, it is very easy to calculate. It has simple inductive definition. So suppose you want to calculate the future reach of this nested temporal formula. So you could just use the future reach of the first part and then add it to the future reach of the next part, and you have the future reach of the entire formula. So having defined the basics, I would now give the formal problem definition. So we have as input a sample consisting of positive and negative piecewise constant signals, and we have a future reach bound, and we would like to synthesize a minimal in size MTL formula that has future reach less than equal to the future reach bound and is globally separating for the sample. So what is this term globally separating? So a formula is globally separating if it holds in every time point for the positive examples and does not hold at some point for the negative examples. So we choose this because in runtime verification, formulas are usually monitored globally on the system. Now, the way we formulate this problem, it turns out there might be situations where there might not be any solution. So for this, we study the decision problem, which checks whether there exists a prospective formula, whether there even exists a solution. So we find out that this problem is in NP, and this is based on a simple characterization of the input parameters that we have, the sample and the future reach bound. And having checked whether there is a solution, we actually look for a solution using an SMT-based algorithm, which gives us a minimal formula. So to our knowledge, we designed the first SMT encoding for dense time logic, which will find formulas of arbitrary structure. In the process, we also show that the problem for synthesizing MTL formulas of a fixed size is in NP. And we have implemented the algorithms in a prototype which is open source, and we used it to synthesize some MTL formulas that we got from CPS, Cyber Physical System Applications. So in the remaining part of the talk, I will give you some insights into the technical contributions, starting with the decision problem. So the decision problem asks whether there exists an MTL formula which can be a prospective solution that is future reach less than k and is globally separating for the sample. So we find out that a solution exists if the sample has a property called k infix separable. So I will explain this property on a very simple sample of one positive and one negative example. So we say x and y is k infix separable if there is a k infix or a portion of y that does not occur in x. So as an example, so here is a portion, two-length portion of y which does not occur in x because there is no two-length portion, whereas like two occurrences of p in x. So we can actually use this portion to construct a globally separating formula. I will not go into the details, but what I will say is that checking whether a sample is k infix separable is in NP. So we can basically guess an infix like this and check in polynomial time whether it appears in X or not. And as a corollary of the previous result, we have that the size of the MTL formula, if one exists, will be bounded by polynomial in the size of the sample and the future reach bound. So having decided whether a solution exists, we search for a solution, and for this we reduce it to a problem in linear real arithmetic. So this is a theory in SMT framework which includes inequalities over real numbers. And the formula we construct in LRA is parameterized by the size n of the formula, and it has the property that it is satisfiable if and only if there exists a solution of size n, and from an assignment of this formula we can actually construct the solution. So what will our algorithm do? It will just go over this psi formulas that we created over increasing values of n till it finds a satisfiable one. Now we have the guarantees that it will always terminate because of our previous decision procedure. We check whether there is a solution, and it will always return a minimal formula because of this iterative process, and we actually the first time it's satisfiable, it returns the solution. Now this formula has 4 different subformulas which have different roles. I will very briefly explain them. So the first part encodes the syntax stack of the formula of size n. So syntax stack is basically a tree-based representation of the NTL formula, and this formula would basically say simple properties of the syntax tree, such as every node should have one operator or proposition, a binary operator should have 2 children, unary operator, one child, and so on, like basic properties of a syntax tree. This part, GSEP, ensures that the formula that we have is globally separating. So it ensures that it holds at every time point in the positive examples and not at every point in the negative examples. This part ensures that the future reach of the formula is less than or equals k, and this essentially encodes the inductive definition of future reach. Now we get to the most complex part, which I believe to be the most complex part, is that this part which ensures that the semantics of MTL is followed when we interpret it over this of the executions that we have. Now this is different from the existing work because when they did the encoding for LTL, LTL is interpreted over discrete executions, but we interpret MTL over continuous signals, piecewise constant executions in particular, and this makes a difference. And to get into the details of this, I would briefly explain how the semantics of MTL works on a signal, and I will take an example signal. It's a signal from one of the previous slides that you have seen. And I would like to calculate which points the formula P holds. So this comes from the definition of piecewise constant signal. So P would hold in this first interval 0, 1 and the interval 2, 4. I have written them down as a union here. Now I would like to calculate where the formula f of 0, 0.5 P holds. Now these are those points from which within 0.5 time points I can see a P. And this can be calculated by subtracting 0.5 seconds from the starting time point of the interval where P holds. Now this is a simple calculation, but the systematic calculation was studied by Mahler and Nikovich, who said that you can inductively calculate this over the structure of the formula. So if you know the intervals for phi and psi, you can calculate the intervals for phi or psi by simply taking a union of the intervals. You can calculate not phi by negating the intervals of where phi holds. The temporal operators, for example, f, a, b, phi, you can calculate by shifting the intervals of where phi holds. G, a, b, phi, you can calculate by negating the intervals of where f, a, b, phi holds, and very interesting relations like this. So in our case, we do not know what the formula is, which means we do not know also what the intervals are. So what we would do is we would use real variables to encode these intervals, and we would impose these relations that were devised by Mahler and Nikovich using various LRA formulas. So we would use LRA formulas to encode union, complement, and all of these operations that you see here. So overall, our formula that we construct is polynomial in the size of the prospective formula, the solution, the sample, and the future reach bound. Which means if we want to check whether there exists an NTL or formula which satisfies the future reach bound and the globally separating for S and also has a size n, this problem is also in NP. So we have implemented our algorithm in an open source tool, and we used Z3 as the SMT solver. And we picked few MTL formulas from applications that we found, and we generated synthetically generated benchmarks based on these formulas to check whether our tool can recover the formulas. And here I present the charts where it shows the time versus, so here it shows the number of signals that were used in the sample, and here it shows the length of the signals in the samples. So what I want you to focus on this is that, so we were able to synthesize formulas for a large number of benchmarks, and we would time out only when the formulas were larger in our benchmark set and had a large sample as well. So in conclusion, I proposed a novel way of synthesizing specifications for runtime verification applications, and I showed an SMT-based algorithm which has theoretical guarantees for synthesizing MTL formulas, and we have implemented a prototype of this algorithm. And in future, we would like to add heuristics to improve the scalability of the algorithm. And we would like to add features to the algorithm in terms of robustness to noisy data, ability to handle different kind of structures of formula. And we would also like to extend it to signal temporal logic, where the propositions are real valued in some sense. Thank you for your patience.
There's a question.
What do you guarantee at the end with your formula? That it works for the example that you give, but nothing more?
Yes, so there are a few guarantees. So it will work So it's an exact separation, so it will satisfy all the it's a globally separating formula, so it will hold at all time points of the positive example and not at some time point in the negative example. Also, it will be the minimal formula which one can get. It will satisfy the future reach bound.
If I add one more example,
so
it might fail.
Yes, it could. Yeah, if you have one more example which it does not satisfy, then it will fail. So this is.
So you will redo it.
Yeah, but,
So what you are referring to is kind of like an active learning setting. So yeah, so this have not been studied so much. This is like a very open area of synthesis of formulas. Passive learning is being studied, but in the future there are also plans to work on active learning where you can modify it. Like.
So I wanted to ask, the NP hard problem, K and S are part of the input, or this is for every K and for every S this is going to be NP hard?
So K and S are part of the input. So it is not known like for fixed K and fixed N what happens. So yeah, it is not. So first of all, these are not hardness results. So these are only NP results, which means that we do not know the hardness of this problem.
So on your previous slide, I think it was the previous slide, you said that you took the formulas from applications.
Yes.
What do you mean by that?
So there is a work which identifies useful MTL patterns, and this is like a collection of. So this is a survey work which looked at like past 10-20 years of research that has been done, and they looked at patterns, MTL patterns which appear in practice, and they identified a list, and we took the list which match which are globally separating, which have this G something form, and we try to check whether our work can replicate that.
Okay. Any more questions? If not, thank you very much.
Thank you.